Okay, thank you. Thank you, Martin, for, I think, a very good structural layout for the session, and especially for the distributed energy resource aspect of the topic. Welcome, everybody. Thank you for the opportunity to speak today. My name's Reddy. I work for American Superconductor, or more commonly we're known as AMSC, based out of Boston, US, Massachusetts area. And I'm going to talk a little bit this afternoon here regarding improving hosting capacity of distribution feeders. We're talking about distributed energy resources and renewable energy in the context of renewable energy. And as you know, we've talked about it since yesterday, about some of the characteristics of renewable energy. They are highly variable and intermittent in their nature. So once you start to kind of integrate those into existing networks, they can actually wreak a lot of havoc. But it's also very encouraging to see how India is actually developing the renewable energy, all the targets and the forecasts that are going on, and I think that's very encouraging. There's a lot of potential, but I think also it is going to have a lot of impact on the grid itself. So it's good to start looking at some solutions and things to integrate that. In that context, I guess just to kind of give a quick overview about the variable energy hosting capacity, existing distribution feeders, they've traditionally been built to be able to supply load. So you have substations that basically take step down from the high voltage supply out there, and then you are running feeders out to your different loads. That's traditionally how this has been. Now you are trying to use those feeders to integrate new forms of energy generation, renewable energy, be it rooftop solar, whether it's community wind, community solar, small, medium, large plants that need to come in. You know, the first opportunity is to be able to maximize the usage, maximize the capacity of that existing feeder. And if you want to do that, the intent is to be able to do that while also maintaining the normal reliability requirements, normal supply quality requirements for your customers out there. So here I'm just kind of giving you a quick snapshot of what renewable energy generation forms can take. So I've got two graphs there, one on the left-hand side that is actually showing a wind farm, small wind farm, and there's a blue curve which is showing almost a very windy day throughout the day, and as you can see, the output of the plant is fairly steady, close to the 100% output for the rest of the day. But if you have, well, you can also, that same plant depicted a behavior that is shown by the variation of the power, which almost went from 100% down to almost nothing. You know, although the scale out there is in the hours, you know, the data that has been taken does not capture the fast changes of that megawatt output. On the right-hand side is actually a 15 megawatt PV solar plant in Arizona, US, that actually has got two graphs out there. The colors of the graphs are not very distinctive, but there's one that shows almost perfect kind of a sunny day out there. The output of the plant is just over 14 megawatts for almost all of the day, and then it kind of ramps down. But then also a kind of a partly cloudy day where you see the output of the plant dropping almost 80%. And when we did the study, actually, we have a system, STATCOM system installed at this plant as well. We did exhaustive studies to understand how fast that change happens, and along with the customer and the data taken from NREL and all that, the impact on the system voltage was just too great for the utility to handle. Really what this reflects is changes of output from renewable plants like this. It has a direct impact on the voltage, depending on the strength of the system, the short circuit ratio, as well as the X on R ratio of the line that's being served. So it has a direct implication on that. So today, your distribution system includes traditional devices such as mechanical voltage regulators that handle voltage changes. So, and as I said, power flow has been designed for basically going from the substation to the load side. The voltage regulators monitor the voltage change, you know, at its location where it is, and if the voltage band is way out, then it actually taps and brings the voltage on the load side higher. You use switched capacitor banks. Okay, that's great. It's actually either switch them in through automatic control, switching controls that you can do, or you can just actually do it on a time of day type thing. But you switch them in and out based on some study or some understanding of what impact it'll have when you switch it in, what impact it'll have when you switch it out with regards to the step voltage change. Also, cap banks, once you switch them in, and then if you don't need it, you switch it out, typically you have to be able to actually let it discharge. So in other words, there's a waiting period before you can bring those cap bank in. And then, of course, those types of limitations kind of does not help your whole cause of actually having more variable generation to the grid. The solution is you could reconductor it, but of course that means that a pretty high cost and then the long lead times to do that. So what we've been looking at, AMSC has been in the business of reactive compensation system since early 2000s, and we've sold over 170 STATCOM systems for various applications, including renewable integration of large wind and solar farms throughout the world. So as part of making the STATCOM system, which is our DVAR STATCOMs for the large systems, we started looking at, how can we take that technology to the distribution system with the advent of a lot of DER coming in. So it's really taking that large traditional STATCOM. If you guys are not sure what a STATCOM is, I'm sure most of you know. But a STATCOM is essentially a power electronic device that's able to provide reactive current in capacitive mode or inductive mode, and that output of that device can be controlled infinitely between the rating of what it is. Traditionally, STATCOMs and similarly SVCs, which is the FACTS devices as they are traditionally called, they are large in size, they're applied in transmission systems. There's none installed in the distribution feeder level because there's a lot of infrastructure, there's a lot of controls and all of this that needs to go. But what we've done is actually taken that technology and brought it down to the distribution feeder level, and what we call is a deployable 1 megavar or half a megavar deployable STATCOM systems that we have developed. A picture of it is actually shown here, and I'll show you an installation picture later on as well. So what you're seeing there is actually a 3 single-phase 11 kV, 330 kVAR STATCOM unit that when you connect all 3 of them, you're essentially having a 1 megavar distribution class STATCOM that can connect directly to your medium voltage line and basically do the same performance as a STATCOM system that would do at a high level. Of course, the difference or the value of this STATCOM is that in the speed of response. It can change, it can actually monitor, and autonomously it can change its output between its capacitive and inductive capability and do it in cycles rather than in minutes or seconds in that case. Obviously, it has a lot of benefit. It can change or it can actually eliminate the use of cap banks, voltage regulators. It doesn't have reverse power flow sensitivity and things like that. And of course, the effectiveness of that control of that depends really on the short circuit capacity and X on R ratio, as I said. So I'm going to move on a little bit just to give you an example of what this is. We've already deployed quite a few systems. We introduced this about 2 years ago. There's been quite a few systems that have been deployed in the US and the UK now as well. I'll show you a quick case study. The paper that we have written on this actually goes through a couple of case studies and details on the technology as well. But this is a 25 kV feeder with generation and load, as well as voltage regulators that are working out there. And basically, at high generation, low load, or at heavy load situations, what we see, the case study, as you can see here, while you want to maintain the voltage between a very nice 0.95 to 105 range, which is what you want to do at all along the feeder, it's not possible in the situations, right? While the voltage regulator does work, there's 2 of them. As you can see, the voltage regulator brings the voltage back up. to within the region, but at the extremes of the days, it does go out significantly, and you are in violation of that. And of course, at light load and generation, you are now on the high side, your voltage gets too high on the feeders as well. So what we've done is basically provide a STATCOM, which works at a traditional, like a machine, on a droop control basis with a voltage set point, and then it helps to keep that voltage, depending on, you choose the ideal location, do some analysis, we can help you kind of identify characteristics of how to choose the best locations for those, and help that to keep that voltage on that feeder kind of within an acceptable band, whether it's a 5%, 3%, 2%, however you want to. It really comes down to the function of how much current do you put in. And the reason is that as a STATCOM, current has a direct reflection on the voltage change that is there. So small distribution feeders, you cannot put 5, 10, 20 megabars of equipment out there. It has to be in the 500 kVAR, 1 megabar type of range to be able to handle and manage the voltage that you have out there. As you can see, this graph shows under the low voltage conditions, what I showed you previously, now it's brought up onto the well within the acceptable range. On the high voltage, it actually does that. So there's no, these devices are now available, and they work in terms of communication, in terms of control, in terms of protection, everything similar to how a large system works, but more so a deployable system out on the feeders of existing grids if needed out there. So in conclusion, basically there are different challenges, and variable energy is going to have a lot of challenges out there. STATCOM, I know it's probably for distribution engineers and all that, it's a new technology. Not only it's deployable, I would very confident to say that it's an affordable technology, because it's something that utilities have already started to consider from that perspective as well. So it is something that I think the technology or tools are now available for you to kind of look at addressing some of these constraints, particularly the voltage constraints that you can see in the grid out there. Thank you.